video in BC Calculus of who knows how many videos it's going to end up being on convergence and divergence tests for series. So since this is our first introduction to series in this course, we're going to start by discussing the difference between a sequence, which we learned about in the last unit, and a series. Essentially, if you remember from the last unit, a sequence is simply a list of numbers that are arranged in some sort of particular order. A series, then, is the sum of the terms in that sequence. So the sum of the first term, or the sum of the first two, or the sum of the first three, and so on and so forth. And so an infinite series would be an expression of the form a sub 1 plus a sub 2. So notice that rather than putting commas between the terms, we are adding the terms. And so the summation notation for that is that it's the sum from k equals 1 to infinity of a sub k. And we usually would have an expression then for that a sub k, some sort of explicit formula for finding the terms in the series. So the partial sums of the series then form a sequence of their own. So like s sub 1 would just be the sum of the first term. S sub 2 would be the sum of the first term and the second term. And then S sub 3 then would be a sub 1 plus a sub 2 plus a sub 3. You kind of get the pattern. Those are called partial sums. So then S sub n would be the sum of the first n terms in the series. The formula for that is a sub 1 times 1 minus r to the n over 1 minus r. So r represents the common ratio if, in fact, the terms in the series are related by some type of common ratio where you're multiplying by a constant. The summation notation for S sub n is the sum from k, not n, k equals 1 to n of a sub k. So if you wanted S sub 5, that would be the sum from k equals 1 to 5 of a sub k. Okay, so those are finite sums, but just like what we did with sequences in the last unit, the majority of the series that we're going to look at are infinite series. So what we do is we say that if the sequence of partial sums has a limit, s, as n approaches infinity, then we say that that series converges to whatever that sum value of s is. And so we write the notation as you see there. Otherwise, we'll say that the series diverges. So what we're looking for is if I add the terms in the series together, do they start to approach a particular number for their sum? Or do they continue to grow and grow and grow and grow, in which case we say that they diverge. So that's what we're looking at in this first portion of our second sequences and series unit. So we're going to look at all sorts of different types of series, and we're going to learn lots of different tests for determining convergence and divergence, and some series you can use more than one test on, and it'll be a personal choice. To begin with, though, we're going to start very basic. I'm not even giving you a formula for it. I'm just looking at, okay, if I had the series 1 plus 1 plus 1 plus 1, and so on and so forth, hopefully you can tell that the pattern is that I'm continuing to add 1 every time. Well, let's think about that logically. Would that series eventually add up to a specific number? Would it converge to that specific number? Well, logically, hopefully you can reason out that if you're continuing to add 1 every single term, well, you're continuing to grow that sum. So eventually that sum is going to reach infinity. So therefore, what we know for this series is that the sum, S sub n, diverges. All right, so then what if we had one like this? Notice that the fractions that you're adding are getting smaller as the terms go on. So would this series, in fact, converge? My answer would be probably yes, because the amounts that we're continuing to add are getting so small that their limit is approaching 0, which means that as I continue to add terms into my series, I'm not really changing the value of my sum that much, because I'm eventually adding a number that's as close to 0 as I can get it. But here's a more mathematical way to kind of come to that understanding, and in fact, even figure out what the sum would be, what these terms would actually add up to. So I notice that the pattern here in this series is that each term is getting multiplied by 1/2. So that would be my common ratio. Another way to find the common ratio is to take the second term divided by the first term. Or you could in fact do it with any two consecutive terms. So the third divided by the second, the fourth divided by the third, whatever. So if I do 1/4 divided by 1/2, I'm going to even do it the slow way, keep, change, flip, you end up with a common ratio of 1/2. Your first term is 1/2. And so your sum would be your first term times 1 minus 1/2 to the n over 1 minus 1/2. Well, that's for the first n terms. For an infinite number of terms, though, our formula is the sum is equal to a sub 1 over 1 minus r. But that only works for a geometric series. And we're going to continue to talk more about geometric series as we move along. So that sum would be my first term divided by 1 minus r. So 1/2 divided by 1/2. So if I continued adding more and more and more terms onto this series and adding those terms all together, they would eventually converge to a sum of 1. The other way that I can look at this and know that it's going to converge from the very beginning is if it is a geometric series, if r is less than 1, then you will automatically know that the series converges. And that's called the ratio test. And we're going to talk more about ratio tests more formally as we get a little bit further along actually in this section here. Okay? But before we get to the ratio test, we're going to look at one test that actually doesn't really determine convergence, even though it says nth term test for convergence. It really more determines divergence. So the way the nth term test works, it says if the infinite series converges, then the limit as k goes to infinity of a sub k equals 0. What that means is that if the limit as k goes to infinity for a sub k does not equal 0, then the series must diverge. So let me show it to you in an example form. If I was trying to determine if the sum from n equals 1 to infinity of 4n squared minus n cubed over 7 minus 3n cubed converges, the only test that I really know at this point, rather than writing out some terms and kind of getting an idea for what it does, is to check the nth term test. So the way that the nth term test works is we do the limit as n goes to infinity for whatever the formula is for the terms in my series. So not even thinking about the fact that this is a series problem, even all the way back at the beginning of the year, if I had given you the limit as n goes to infinity of 4n squared minus n cubed over 7 minus 3n cubed, hopefully at this point you realize that limits to infinity, we can use n behavior models if it's a polynomial in the numerator and a polynomial in the denominator, which this is. So if we just focus on the n behavior model for this, we would have negative n cubed in the numerator and negative 3n cubed in the denominator, which is going to reduce. Your n cubes are going to cancel, your negatives are going to cancel, and so this answer is 1/3. Now what this 1/3 means is that as I continue to write out the terms in my series, so my first term, for example, if I substitute 1 into here, I would end up with 3/4. And then if I substitute 2 into here, I would end up with 16 minus 8 is 8 over, I feel like I did something wrong there. Negative 17, and so on and so forth. And so you would continue to write those terms out. What the limit is telling you is that those terms, the individual term values, are going to approach a value of 1/3, which means that as I add another term on, I'm adding another value of 1/3. And the next term would add another value of 1/3. And the next term would add another value of 1/3. So because my terms individually are not approaching a value of 0, that means I'm continuing to add some value onto my sum. In this case, I'm going to add 1/3 onto my sum every single time I incorporate another term into my series. So that sum is going to continue to grow. We don't want the sum to continue to grow if it's going to converge. So because my individual terms do not approach 0, that means that my sum would not converge to a particular value. So what I've learned from this is because the limit as n goes to infinity of 4n squared minus n cubed over 7 minus 3n cubed does not equal 0, the series diverges by the nth term test. And this is actually how you would have to write your explanation out. For me, or on an FRQ or whatnot, you have to state which test you used, how you knew that that test determined what it was. You can't just say the series diverges. You have to say what test you used and what conclusions you were able to draw based on that test. Okay, so let's look at another one with the nth term test. So this one looks pretty simple. The sum from n equals 1 to infinity of 1 over n. So if we write out some of those terms, that would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on and so forth. If we do the limit as n goes to infinity for that explicit formula, then we get 1 over infinity, which is 0. All the nth term test tells us is that if we get an answer for this limit that's not 0, then the series has to diverge. What it doesn't tell us is if we do get an answer of 0 for our limit, we don't know for sure that the sum of 1 over n would actually converge to a specific value. Our answers would be inconclusive at this point. And so what we would have to do is we would have to use then a second test to determine if in fact 1 over n really does converge or if it diverges. And we're going to learn down the road, once we add some more tests into our toolbox, that 1 over n actually does diverge, even though those terms are getting smaller. This is a divergent series. So one more that would be similar to that would be the limit as n goes to infinity of 1 over n squared. So again, if we tried to evaluate the limit there, we would get 0 for that guy as well. So again, the nth term test would be inconclusive, and we would have to go on to a second test to determine convergence. I will tell you that this one actually converges, and we'll learn tests again down the road that will show us why that guy converges. So I'm going to end the first video here, wrapped up with the nth term test for divergence, and then the next video is going to go into the ratio test and radius and interval of convergence.